Hello guys, welcome back to my channel. Today I'll be doing a crazy product problem. So let's get to it. It's gonna be not that long I think compared to our other weird integral ones. But let's get to it in any case. So we have our question. The limit as n tends to infinity of n to the negative n squared, and in a bracket we have n plus 1 times n plus 1 half. All of that keeps on multiplying with n plus 1 over 2 to the n minus 1, and then everything is raised to the nth power. Now there is only one thing we can do right now. This unbracketed term, uh, n to the negative n squared power, we can write that in a new way. We can write that as, say, 1 over n to the n times n, because there was an n squared. Well, the rest of it remains the same, n plus 1 times n plus 1 half dot 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 n plus 1 over 2 raised to n minus 1, everything that's raised to the nth power. Well, we can do one nice thing over here. We can have 1 over n to the n, that's raised to the nth power, and then everything else just remains the same for now, n plus half dot 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 n plus 1 over 2 to the n minus 1 raised to the nth power. Now, why don't we take everything, because everything is raised to the nth power, why don't we take everything under a common power? So we are essentially going to have this infinite product, almost infinite product you can say, n plus 1 times n plus 1 half dot 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 n plus 1 over 2 minus 1 over n to the n, everything raised to the nth power. Now, one thing that I would like to ask you guys, how many terms are there of these n plus 1 times n plus 1 half till n plus 1 over 2 raised to n minus 1? How many terms are there in the numerator? Well, how do we find the number of terms? We do the last term minus the first term plus 1. So the index of the last term is n minus 1, and then 2 has a zeroth power here, minus 0 plus 1, that just gives n. So there are n terms here, and n to the n is just multiplying n with itself n times. So this is n times. So one observation is there are n terms in the numerator, and n is multiplied with itself n times. So there is n into n times. So if there are n terms and n n's, why don't we distribute each n per term? So one term will have one n. Um, so we can have an n here, for example, an n here, and then an n for the last term. So let's just rewrite everything from these based on these observations. So we're going to have the limit as n approaches infinity and in bracket we have n plus 1 over n. I'm writing this as one term with these brackets, and then we have n plus 1 by 2, everything divided by n, and then for the last term we have n plus 1 over 2 raised to n minus 1 divided by n, and everything is raised to the nth power. Now let's do some cleaning up inside these brackets. We have 1 plus 1 over n times 1 plus 1 over 2n, and then finally 1 plus 1 over 2 raised to n minus 1 times n, everything that's raised to the nth power. Well, can we express this more generally? Because it's a product, can we use a more compact notation? Because trust me, it's really exhausting to write these dots and these large brackets every time. So the limit as n goes to infinity, and then let's define a product. This is the symbol for a product. The sigma was for a sum, this is for a product. From k equals 0 to n minus 1 of 1 plus 1 over 2 to the kth power times n, but raised to the nth power. So great, so you can check. So when k is 0, we have 2 to the 0th power, which is 1. So 1 plus 1 over n to the nth power. Yes, we have the first term in place. Then when k is 1, 1 plus 1 over 2 times n. Yes, we have our second term in place. And then for the last term, you can check n minus 1 instead of k. So everything matches. So it's great. We can use this notation. Now notice that our limit problem, our entire term is raised to the nth power. This product is, you can say, raised to the nth power. And how do we tackle limit problems that have an exponent, an exponential variable like this? Well, we take the log on both sides, right? So first let's just call this y, and I'll take the log on another page. So see you there. So this is what we define to be y. So let's take, as I promised, the natural log on both sides. So ln of y, we're going to have the natural log of the limit, and since it's continuous, we can have the limit of the natural log. So the limit as n goes to infinity of the natural log of this mighty expression from say k equals 0 to n minus 1 of 1 plus 1 over 2 raised to k times n, that's raised to the nth power. Now we can use one property of logarithms. Say we have the natural log of x to the 8th power. This is nothing but a times the natural log of x. So basically whatever our argument was raised to, we can just bring that number down and multiply it with the logarithm. Now over here, the argument indeed is this product of this term, and that is indeed raised to the nth power, right? I'll just use parentheses properly so that you can see that the argument is raised to the nth power, right? Wait, let me write this properly. So as you can see, inside the parentheses, this argument of this product is raised to the nth power. So let's bring it down now, because we know our properties. Limit as n approaches infinity of n times the natural log of this product, some say k equals 0 to n minus 1, 1 plus 1 over 2k times 2 to the kth power times n. Now let me remind you before we do anything of another log property. Say we had natural log of a times b. You can split this, decompose this into the sum of two separate logarithms. So natural log of a into b becomes the natural log of a plus the natural log of b. So let me just generalize this result. So say we have the natural log of say products from say j equals 1 to a, for example, and we have b sub j. You can decompose this into a sum that runs from j equals 1 to a of the natural log of b sub j, right? I mean, this is essentially the same logic that we are applying here. So instead of just writing a product of two terms, say we have a product of a terms, and a is like an arbitrary number. So you can split this into the sum of a logarithms. So let's apply this great property now. So in a way, logs are a great way of converting our products into sums. So we have the limit as n approaches infinity of n times. Now we can take the sum from k equals 0 to n minus 1, sum of the log now. Instead of the log of the product, we can have the sum of the log of argument. Well, it remains unchanged. So we have 1 plus 1 over 2 to the kth power times n. Well, great. We have our limit as n approaches infinity. We can just take the n inside k from the sum from k equals 0 to n minus 1 of the natural log of 1 plus 1 over 2k times n, and we have this thing multiplied by n. Now let's just plug in the value of infinity and let's see what is really happening over here with the function. So when n approaches infinity, this thing will go to 0. So we'll have the natural log of 1, which is 0, and we're going to have an infinity here. So 0 times infinity, it's pretty indeterminate. So why don't we write this indeterminate form in some sort of acceptable form, says infinity by infinity or 0 by 0, so that we can apply our L'Hopital's rule. Otherwise we can't do much with this limit. So what if we write the numerator as it is, ln of 1 plus 1 over 2 to the kth power times n, and instead of multiplying n directly, why don't we write this as 1 over n? Because look what happens, the numerator, say n approaches infinity, this thing will go to 0. We'll have the natural log of 1, which is 0, and then 1 over n also goes to 0. So we have basically a 0 by 0 situation with us. And what does that call for? That's right, L'Hopital's rule, the most powerful limit calculating technique, I think. So what do we do to find the L'Hopital's rule? To apply L'Hopital's rule, not to find, to apply L'Hopital's rule. So say we have an initial natural log of y. To apply L'Hopital's rule, we differentiate the numerator and the denominator. In this case, we need to differentiate with respect to n, because n is approaching infinity, right? This sum is just going to be there. So we have the limit as n approaches infinity. Sum is going to stay the same. The sum from k equals 0 to n minus 1, and then we have to differentiate natural log. We get 1 over the argument, which is 1 plus 1 over 2 to the kth power times, and then the the derivative of the argument. So basically the derivative of this inside part, derivative of 1 is 0, 1 over 2k is a constant with respect to n. You can write that as it is, and then the derivative of 1 over n is negative 1 over n squared. But don't forget to differentiate the denominator. Again, we have to differentiate 1 over n, so we get negative 1 over n squared. Yes, it looks like a mess, but the great part is this is cancelling out with this. Let's just clean this up a bit. So we have the limit as n goes to infinity of the sum from k equals 0 to n minus 1 of when I clean this up a little bit, I'm going to have 1 over 2k plus 1 over n. Now it's finally time to apply this limit, and when I do that, on top there's an n. Notice that. So say if I substitute like infinity, treating infinity as a number, that's actually not quite mathematical, but in our case, for your explanation, I'm treating it as a number. So infinity minus a small finite number like 1. So infinity minus 1. If you take something out from a really big thing, it doesn't really change that big thing, right? So infinity minus 1 is infinity. If you know were to treat infinity as a number such that you can plug it in a variable and stuff like that. So you can say on applying this limit, we obtain the sum from k equals 0 to infinity, and then again 2k plus 1 over n, and when n goes to infinity, this thing goes to 0, right? Because the denominator grows really large and the fraction becomes 0. So finally we have the sum from k equals 0 to infinity of 1 over 2 to the kth power, because this thing just went to 0. Now what does this look like? If you want, I can just write it down. So when k is 0, I have 2 to the 0th power, which is 1. So 1 plus when k is 1, I have 1 over 2, and when k is 2, I have 1 over 4. That goes on till infinity now. Well, what does this look like? Yes, that's right. A geometric series. Infinite geometric series actually. So let's evaluate this geometric series on another page. See you there. So previously, because of earlier calculation, we evaluated that the natural log of y gets reduced to, well, we got rid of the limit now, didn't we? So sorry for that, we don't need this. So basically it got reduced to this infinite gp from k equals 0 to infinity of 1 over 2 to the kth power. Just having a common power enables us to write 1 over 2 to the kth power. Now the first term a, when you plug in k as 0, is 1, and the common ratio is r. Common ratio r is a half. What's the condition for convergence of a geometric series? So the condition for convergence demands that the absolute value of r be less than 1, and r 1/2 is definitely less than 1. So our condition is satisfied. So our geometric series converges, and we can use the convergence formula that we have there. How we find out the answer to the infinite geometric series. So we have sum from k equals 0 to infinity of 1 over 2 to the kth power. What's the formula? It's a over 1 minus r, right? What's a? 1 over 1 minus r is a half. So that just makes this thing 1 over 1 by 2, which is 2. But remember that 2 is nothing but the natural log of y, right? Because we took the natural log initially. And why don't we raise everything to the eth power? So e raised to the natural log of y is equal to e squared. And by properties of exponents, these two sort of cancel out because they're inverses of each other, and y is equal to e squared. Well, quite a satisfying result now, isn't it? So in conclusion, what's y, you ask? Well, let me remind you, in that case, y was the limit as n approached infinity of the product from k equals 0 to n minus 1 of 1 plus 1 over 2 to the kth power times n, the whole thing raised to n, that is equal to e squared. But why don't we write this in the original form that we received our question? The limit as n approaches infinity of n to the negative n squared power, and then in bracket we have n plus 1 times n plus 1 half dot 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 n plus 1 over 2 to the n minus 1 power, everything raised to n, that is equal to e squared. Well, there was actually a quicker way of doing this problem, because from this step, if you could separate everything out, say limit as n approaches infinity of 1 plus 1 over n times n, and then the same thing, limit as n approaches infinity of 1 plus 1 over 2 over n raised to n, say for say n minus 1 terms. This thing by definition is e, this thing is e to the half power, and then in the limit as n goes to infinity, n minus 1 also tends to infinity. So in a way this would have become some sort of infinite uh, infinite product over here. Let's write that this way, and then say if you could use exponent properties, we would have obtained e raised to 1 plus 1 half plus dot dot 1 over 2 to the kth power. Everything is in the power, and then knowing that there is a gp on top, you could directly apply the gp formula. What's the first term? A is 1 over ratio is half, so 1 minus half, that yields 2 e squared. See, you could have directly done this, but I actually wanted to show you the entire process, because there was this fascinating part of converting this product, this infinite product of sorts, into this infinite sum by virtue of the natural log function, and then using L'Hopital's rule in a sort of healthy way that we do to solve limit problems completely. So this is a quite a wholesome process. I've shown all the steps, and I hope you followed everything, because everything is quite intuitive if you ask me about this problem. So that's it for this video, guys. Please like, share, subscribe, recommend me to your friends who you think would be interested in this sort of mathematics that I do, and have a great day. Peace out.